In last term, we have studied that when current carrying conductor is placed in magnetic field, it experiences a force. And today, we will determine the torque acting on a current carrying conducting loop when it is placed in magnetic field. We will see that if the loop is placed parallel to the magnetic field, it experiences a force that tends to rotate it. So today we will derive that. In electrostatics, we have studied there is electric dipole separated by a distance d, and electric field is in this direction. Then this dipole experiences a torque. Same thing we will try to find in case of the magnetic field in which a current carrying loop is placed. We know that when current carrying loop is there, it forms north and south pole, that is magnetic dipole. And when a magnetic dipole is placed, in that case, in magnetic field, we will try to find the torque on that. So let us consider the similar behavior here in magnetic field. This is magnetic field B. A loop is, current carrying loop is there. Current, assume that current is flowing like this. Here the field is in x direction and the loop is, conductor is placed in xy direction, and this is z direction. Okay, if we have this configuration, then before coming to the torque, let us try to find how much force will be experienced on this loop. So consider few points there, A, B, C and D. So there are 4 sections, try to find the force acting on them. So force at this section, part of the loop, force at this part of the loop, force AB will be, we know that IDL or IL cross B will be the force, and from there the current that is flowing in this loop is I, length of the part is AB, and AB B cross product will give you sine theta. Theta is the angle between this and this. So here we find that IL is in the direction of minus x. From here we can find this is x direction and this is minus x direction. Okay, and B is, this is AB, IL, and B is in plus x direction. So the angle between these two is 180 degree. The sine product will give you 0. So the force acting at this part will be 0. The force acting on the part BC will be, if BC will be IL cross B, I is the same current that is flowing there, LBC is the length of this side, and B sine theta. Theta is the angle between B and this is the direction of B, this is the direction of BC. So this is y direction. The cross product of y and x will give us the z, negative z direction. Okay, because we know that this is x, this is y, this is z. Like this, the cross product of x and y give us z, and the cross product of y and x will give minus z. So the output will be ILB in the direction of minus AZ. This is the force acting on this part. Similar to this, the force acting on this will be 0. CD will be 0, as the angle between IDL or IL and B is 0. So force at this is 0, and the force at FDA will be ILB sin theta. Again, this B is in the direction of x and IL in the direction of minus y. The cross product of IL, that is in the minus direction. By the way, this IL will be in the direction of IL minus AY, and B is in the direction of, if we take from here, that is IL cross B. Then from there, B is in the direction of BAX. IL is in the direction of minus AY, cross B in the direction of AX. So the cross product of AY and AX will be minus AZ, and that minus and this minus will be plus AZ. So it will give us ILB in the direction of AZ. Okay, so if we find the net force acting on this loop, then F total will be FAB plus BC plus CD plus DA, the total force, force between this plus force between this plus force between this, and so on. So combining all, it will be 0 plus ILB in the direction of minus AZ plus 0 plus ILB in the direction of plus AZ. Any loop is there, the force, net force is 0 in the loop. Okay, that we have find from here. Now, if we wish to find the torque, then we know that torque is R cross F. R is the radial distance from the axis through which the torque is force is applied. So for this loop, we have to assume axis first. For example, consider this axis, and we have to find the torque at this loop, considering this as axis of the force. So for that purpose, we will try to find the R cross F for full force acting on this. So for let us start from here. Okay, for this portion, RF sin theta. So as F is 0 for this and this portion, so torque at this portion will be 0. There will be no torque acting at this portion. So the remaining part that we have left is R cross F at BC. Okay, so at this portion, the torque that is acting, r is the radial distance from the axis where it is assumed as hinged. So r is W by 2. The force is at this portion, force is acting downward minus AZ direction. So ILB in the direction of minus AZ and R is in the direction of minus AX. From here we can find it is minus AX. So R is in this direction minus AX and the force is acting downward, that is minus AZ. Force is in this direction. So the cross product of this and this will be, the cross product of this will be minus AY. Okay. So from here we will find it is WLBI divided by 2 in the direction of minus AY. Okay. This is the torque acting on this. So this portion is having torque 0, this portion having torque this portion having torque 0 as force is 0 in this portion. Now come to this part. So torque at dA, it will be again R cross F. R is in the direction of X, that is W by 2. W is the width of the loop. W by 2 in the direction of X cross. F is at this portion, F was in the direction of Z. So it will be ILB in the direction of Z. So from, if we multiply, then we find WLB, I is left. So I divided by 2, AX cross AZ. Apply same, AX cross AZ. It will give us minus AY. So it will be in the direction of minus AY. So if we try to find the total torque acting on this, then that is, the torque will be the sum of these two plus TDA, remaining two are 0. So we are considering only these two. It will be ILWB by 2 will be full and it will be in the direction of AY. Okay. So this is the torque. If we will simplify this, then what we can say, L multiplied with width. L is this, width is this. So it will give us area B in the direction of AY. Now, if we reform this mathematical statement in such a way that the direction of this remains minus AY, so for that purpose we can write IA minus AZ cross B in the direction of AX. So its multiplication will give us IAB, that is this, and AZ cross AX will give us AY and minus will be there, so it will be equal to this. There will be no change at all. And what is this? This is nothing, just magnetic dipole moment. So this is known as M cross B. Okay, this is the torque. Torque is equal to M cross B, where M is magnetic dipole moment, and if we further define this, then it is the product of the current and area of the loop, and the direction of this is the normal to the loop. So loop is this one. So area vector will be the normal to the loop. Loop is anti-clockwise, so normal should be downward, that is minus AZ direction, and B is in the AX direction. So this is magnetic dipole moment and this is the magnetic field. So the final result will be torque is equal to M cross B. Now let us solve one example to find the magnetic dipole moment. The problem is determine the magnetic moment of an electric circuit formed by the triangular loop shown in figure. So this is the loop. Okay, now we have to find the magnetic moment for that. And from here, M is the current and the surface area in the normal direction. So from here we can say M is current, surface area and AN. So the important point is current is known. To find S, the surface area and the AN. And if we talk about the surface area, then this is nothing the area of the loop. So that is any triangle, we can have half into base into height, we can say from here. So from here we can find the area, that is half, base is, this is 2, this is 2. So this will be 2 root 2. So base is 2 root 2. And to find the perpendicular distance for this plane, we can have this by 2 because it will be perpendicular, because this is equilateral triangle. So it will be 2 root 2 by 2. Hypotenuse, base, it will be perpendicular. That will be 2 root 2 multiplied with square minus 2 root 2 by 2 square. It will square root will be this height. So from here we can get 8 minus 2 square root 6. So here it will be square root 6. The area will be root 12. Okay, and now we know I, we know S, AN is required to know. So for finding the NO, just we have to find the function of the plane. So the function of the plane, as it is 0, 0, 2, 0, 0, 0, 2, 0, 0, 0, 2. From there we can find, it can be written as x plus y plus z is equal to 2. This equation can satisfy this plane if this coordinate, the coordinates of this and this are 2, 2, 2. Then from there we can find the plane equation, and for any plane, if we wish to find the normal vector for that, then we can have the del of that plane divided by the magnitude of that absolute value. It gives the normal to that. If it is clockwise, the normal will be up. If it is anti-normal, will be down. So as it is up, so it will be positive here. So del F will be, if we find the del F for this, for this function, then we know how to find the del F. That will be AX plus AY plus AZ. If we find the del F for this function, then we can have this. And the absolute value of this will be the root 3. 1 square plus 1 square plus 1 square cube root. That will give us the unit vector in the direction of this plane. The direction of this plane. So we have AN now, we have S, and we have I. So we can find the magnetic moment, that is I root 12 root ax plus ay plus az divided by root 3. So if we will this the direction its unit is ampere meter square. So we can say ampere meter square. If we will simplify, then it will be 5 into 4 into 3. 4 will be out, it will be 2. 2 root 3 ax plus ay plus az divided by root 3. So from here we can get 10 ax plus ay plus az ampere meter square. So this is the magnetic moment for this system. So for today, we can stop at this point. Tomorrow we will start next topic. Thank you.